Okay. Just gonna make sure my audio is okay. I'm listening on my phone. Seems all right. Let me get this off. Close out of that. Okay. Well, welcome. That's a little small. I'm gonna lose some clarity, but let me make this larger. Oh, that looks okay. Okay, so today sorry, just messing with my tech. Today, I'm going to look at solving this problem, and basically it comes down to proving that all norms on finite dimensional vector spaces are equivalent. So I got the title at the bottom, so that when I'm deep into this thing, if anyone joins in the middle, they at least know what the goal is. And yeah, a few caveats. This is just a problem that I looked at earlier this week. I'm studying for the analysis qualifying exam that I need to take. Analysis is not my best subject, and I do not claim to be an expert. So there may be mistakes or things that I don't explain super well. I didn't necessarily prepare anything extra for this talk other than my solution. So I'll try to talk about stuff in more detail, but it will be off the cuff. So if you are watching this either live or after the fact, if I make any mistakes, please let me know, and I will make note of that. So let me read through the problem, and if you don't know any analysis, it probably will not make a lot of sense, but I'll try to give some background before we really get into it. So the problem states two norms, which we'll call norm 1 and norm 2, and these symbols are the symbols for norm. The dot just means we could put vectors in there, and we take the norm of the vector. So two norms, norm 1 and norm 2 in a vector space X are called equivalent if there exists positive real numbers, capital C greater than lowercase c, greater than 0, such that for all x in the vector space X, c times norm 1 of x is less than or equal to norm 2 of x is less than or equal to big C norm 1 of x. Our goal is to show that any two norms in Rn are equivalent. Problem also states to give an example of two non-equivalent norms in infinite dimensional space, which I don't think I'm going to do. We're just going to focus on the first part. That's plenty long enough. So what the heck is a norm? A norm is pretty much just our idea of like a length of a vector. It's just one way to talk about length. So let's say we're in a two-dimensional space here. So let me get our some axes. And if I've got a vector, which I could call x, whoa, I'm using a tablet to write, but if I put my hand on it, it writes stuff I don't want it to write. Oh, it's doing it again. All right, you gotta be very careful. X, I did it. All right, so this is vector x. Then we could, the norm of x is just some idea of length. And I'm going to put length in quotation marks because there are different ways we could consider length. Now, the way that you might be considering length, like if this point is AB, then we could look at this triangle where this is A and this is B, and then we could call the length the square root of a squared plus b squared. Following the Pythagorean theorem, that would be the length of this vector right here. This is what's called the Euclidean norm. So it's, works like you learned geometry in high school. But there's other ways we could do it. I could just say, and since norm 1 and norm 2 are things that were just stated in the problem, I'm going to call this norm 3. Although I've seen it called norm 1. And I don't know if that's canonical or not. I've seen it in a couple different places called norm 1. In any case, I'm going to call it norm 3. What if we just had a plus b as a norm, as a length? Just say, take the coordinates, add them up, and call that the length. Now that doesn't sort of operate the same way that our intuition says, but given some rules we're going to set out about what a norm has to satisfy, which I'll show you in just a second, this follows those rules, or more specifically, if I were to say the absolute value of a plus the absolute value of b. And we'll see that right now. All right, let's get, I have too many screens. I can't have everything up at all times. All right. So first off, everything I'm going to talk about as far as like this proof, I got from online, from something I saw from MIT. It's Notes on the Equivalence of Norms by Stephen G. Johnson, MIT course from 2012. So I did not come up with this. I just sought to understand it. So credit goes to Stephen G. Johnson for this proof. So actually, before I talk about norm, I'm going to formalize this norm 3 here. I'm going to call norm 3 well, actually, let me be more careful. Before we get going, let's have any of our I was making sure we're in Rn like I thought. Okay, let's have just any x in Rn be written oh, that is weird. Is this showing up okay? It's showing up okay. So we're going to write any x as sums of ai times ei, where ai is just a real number. Oops. So ai is just a real number, and e1 to en is a basis of Rn. So this will work for any basis. I mean, you could have E1 be 1, 0, all zeros. You could have E2 be 0, 1, 0, the rest zeros, etc. That's like the standard basis. But this will work for any basis. We're going to keep it very general. do need to blow my nose 1 second. I'm back. Okay. So, I mean, like this vector here, we could have written as, it's going to be messy. Could use different colors. I don't know if I'm that fancy. So this vector here I could have written as a times 1, 0 plus b times 0, 1. And that equals AB. Same idea here, but we don't need these to be our basis vectors. You just say they're basis vectors. There's, I believe, many ways we could make a basis for Rn. Anyway, so now that that's out of the way, let me formally define this, what I'm going to call norm 3. I wonder if I use my sweatshirt if it will not think I'm touching. Ooh, that might be working. What a hack. Okay, let me get my notes back up. Actually, I think I can I do this? Movie magic. Okay, other than I can't point at things. Not movie magic. Is it time for a 3-screen setup? It feels like it. All right, we're just defining this just like how we defined it up here. It's just going to be the sum of the absolute values of each of the coordinates, because these numbers kind of act like coordinates based on our basis vectors. So these AIs do the same. So it's just going to be the sum as an equal. I need to fix that. It looks like a less than or equal to, and we're going to do that a lot. All right, so this is just the sum of these AIs, the absolute value of these AIs. So our goal now is to show that this is a norm. And maybe before I continue, I should give a brief outline of what we're going to do. This is what I meant to prepare earlier, and I didn't. But I've got the paper I can look at. So we're going to show that norm equivalence is transitive. So we're going to show that if these two norms, norm 1 and norm 2, are both, we're going to say if they're both equivalent to norm 3, which I do have to show as a norm, so that's like step 0. But if they're both equivalent to any old norm, really, then they're equivalent to each other. So we got to show that. That'll be nice. The next thing we're going to show is that we only have to look at vectors that are unit vectors, so length 1. So unit vectors, vectors of length 1. Basically, we'll say if this is true for unit vectors, it's true for all vectors. And when I say this, I mean this sort of inequality here. And that's easier than it looks. The next thing seems a little bit out of left field to me, but it will allow us to use a theorem that's very handy. We're going to show that any norm is a continuous function, because I'll show you in a second the definition of norm, but a norm is a function that takes a vector and gives you a length, a number. So an input, our vector, and then it outputs the length. It's a function. So we're going to say that any norm is continuous, a continuous function under this norm 3. Although if you look at the paper I mentioned, it is called norm 1. We just had to have a norm 1 in this problem though. And then our last step will be to, since we can consider just unit vectors, we look at the maximum and minimum on a unit sphere. Boop. Hello, Mish. If you're here for math, you're in the right place. Anyway, this is our outline for the proof. The first thing we got to do is show that this is a norm. So let me fly in the definition of a norm. So again, norm is basically an idea of distance, and so we want it to satisfy some stuff that we want what our ideas of distance to satisfy, even when the particular definition of distance might not be what we expect. So let's look at this definition. A norm on a vector space V is a map, and you can see the symbol there. So it goes from the vector space to the real numbers specifically, satisfying 3 conditions. So the norm of a vector has got to be a non-negative number. We don't want negative distances, and we only want a 0 distance if our vector is 0. We don't want something that, you know, appears to have length because it has, you know, coordinates, non-zero coordinates in whatever basis we're in. We don't want that to be 0. That was pretty straightforward. Number 2, if we take a scalar, so this is just a scalar, we could say it's a real number, but whatever the scalar is in our vector space, and multiply it by our vector, then take the norm of that, we're going to get the same number as if we take the norm of the vector itself and then multiply by the absolute value of that scalar. We'll see that in action when we prove this is a norm in a second. But basically, well, we can say out loud back with our original example. Basically, if I took this this point AB and multiplied it by 2, so I had 2A, 2B, then that should have twice the length of original vector. And that's an exercise for you. It does. Last thing is this inequality here. Make sure that it is visible, not behind my face. Is this inequality here? It's called the triangle inequality. It's called the triangle inequality because it acts like a triangle. We want, if you know, if this is our vector v plus w, and like this was v, and then if I transpose w, if you've done some vector addition, you can look at going tip to tail like this to add vectors. We want the length of this, I'm pointing with the wrong thing. We want the length of the v plus w vector. It can't be bigger than the lengths of these two vectors combined, because otherwise then they can't form a triangle like this, and then it sort of breaks our ideas of what these vectors are doing. We want it to meet this triangle inequality. Triangle inequality is the tricky part of norms, but then it's also once you have a norm, it's a very powerful part of it. So it's a good thing to have in our definition. Okay. Can I think I can. Could I do it here? I just want to move this down here. Nope. I'll just get rid of my definition of a norm. Why is it not letting me undo? Okay, put that back in there. Sorry, I tried to do something I've never done before. But I have a different method here. This may look weird. I'm taking a picture of that, and I will move it down here. The grid doesn't line up, but that's okay. Or does it? No, it doesn't. Okay. So we want to show this as a norm. Let's see. So again, we're taking basically the coordinates, absolute value of the coordinates based on the basis vectors, but you could think of them like coordinates, and adding them up. So is this a norm? For the first condition, it's pretty clear to see that it is. When we take the absolute value, we're going to get positive numbers, adding them together, still positive. So the first part checks out. And then the only way it's going to be 0 is if all of the coordinates are 0. If all the coordinates are 0, then it's the 0 vector, no matter the basis, because everything just goes to 0. So 1's done, just verbally. 2, we can do this. So let's let so this is for proof of 2. Let's let R be a real number, because Rn is our vector space. Yeah, that's fine. R is our scalar. This is one spot where I may be making a slight error, but it won't really affect anything. So we want to look at R, I'll say Rx. And we want to show that this is equal to absolute value of R times norm 3 of X. So we're going to use this definition. So first off, if we're multiplying X by R, then we're multiplying each coordinate, if you will, by R. So if we apply the definition that's right here, we're going to get the sum of the absolute value of R times AI. So I'm just applying this definition. Since we had Rx here instead of X, we get RAI instead of AI. So far, so good. Now, absolute value of RAI is the same. This is the same as just absolute value of R times absolute value of AI. And that's an exercise if you're not convinced. But since in the summation, there's this common factor of absolute value of R, we can pull that out. We can factor it out of this sum, and we'll get absolute value of R. Keep accidentally pressing a button. There we go. AI. Make sure everything is still visible. It is. And then we can see, oh, look at this. This looks exactly like this. And so this is our absolute value of r times norm 3 of x. That's what we wanted to show. So 2 is done. Let's see. Do I want to go through 3? Not really. Well, I will real quick. This might be longer than I want, but I can always hand wave later. My goal was to have this be an hour, although I guess I started at like 12:10. But I haven't really started the proof proper yet. So that's a little worrying. It's proof of the triangle inequality. So that means we want to start with like x plus y, and we'll want to show that this is less than or equal to norm 3 of x plus norm 3 of y. So let's see what this looks like. Let me just make sure I'm not going off the screen. Okay. Here, I'll just get the norm at the top. Perfect. All right, so I'm just going to apply the definition of how we were, how we called like a vector in this space. That was based on our basis. So that means we're taking the norm of these sums of things. And I'm just going to stop doing the these bits. Just we're always going over all I from 1 to n. So just assume that's the case. All right, so x, we'll say the coordinates were the AIs, and y, let's call those coordinates BIs just for, so we can tell them apart. But they're still both based on the same basis. All right, well, this is just like A1, E1 plus A2, E2, so on. This is B1, E1 plus B2, E2, and so on. So we can group, like there's an A1, E1 and a B1, E1. We can group those together. And we'll just by adding, these coefficients. We can do that for each I. Oops. Still norming this. Norm. All right. So we've done that. And now let's apply our definition of a norm. This is just new coefficients on EI. This is like x plus y, we could consider z. We could call x plus y z. AI plus BI are the coordinates for each I. So we just apply the norm. Let's go to the next line, I guess. On the tablet I'm writing on, it's not as big as the screen, so I have to scroll back and forth. Learning process. Anyway, we're applying the norm, so it's just we're adding up the absolute value of the coordinates of these coefficients, which are AI plus BI. Bam. We're not done yet. We haven't done this inequality yet, but absolute value is just the Euclidean norm on our like one-dimensional real number line, right? Absolute value is your distance from 0. So it's your Euclidean norm. It's the distance that you expect. We know that this is a norm. We know that it satisfies the triangle inequality. Therefore, we can apply the triangle inequality here, and that will give us what we want. We basically turned it into something where we already know we can use the triangle inequality, and so then we're good. So with the triangle inequality, we get this. I can write it out real quick. I thought about not. but I'll do it. Triangle inequality lets us do this. Triangle inequality on the absolute value. We can't use triangle inequality on the norm to prove the triangle inequality on the norm because that doesn't make sense. Anyway, but we can see here, oh look, that is the norm 3 of x. This is the norm 3 of y. We get what we want. Cool. All right, this thing's a norm. So we can now start applying our proof here to show where did my problem went away. I can get that back pretty quickly. Oops. Yeah, there we go. All right, so, and then our eventual goal is to prove that any two norms, norm 1, norm 2, are equivalent. Cool. First, we want to show that norm equivalence is transitive, and we're going to are we going to specifically use norm 3? We're not. We don't need to do that. This is more general. So I'm going to grab two new norms just so I don't confuse them with norm 1 and norm 2. I probably don't need to go to this level of generality since norm 1 and norm 2 are general, but I'm about to assume that these are equivalent to something. So we're not assuming anything about norm 1 and norm 2 yet. So this will be our part 1 based on our outline from before. So we're going to let these two new norms, I'll call them norm A and norm B. Let's say they're both equivalent to norm 3. So our goal to show this transitivity is that we're going to say that, okay, oh, we did use norm 3. I'm going to keep it norm 3 so it matches with my notes, since our goal will be to use that norm 3 specifically. However, everything in this piece 1 does not rely on it being specifically norm 3. I could have taken and called this norm C, any old norm. Can that go away? Go away. Put you up here. So yeah, this doesn't have to be norm 3. It can be any norm. It's illustrative because we're going to use norm 3 later, but I didn't use it in this part. Anyway, so since we have this equivalence, then by the definition way back in the problem, we've got these sets of constants. So we have, so there exists, this is the symbol for there exists in case you don't know. We've got, I'm going to call it a big CA, which is greater than a little CA, which is greater than 0. And we'll do another set. We got these two norms that are equivalent to this other norm. So we need two sets of these constants such that ST is how I say such that. Some people use periods, but I don't have time for that. All right, this is a long string. So this is just based on the definition of equivalence. We've got CA norm 3 less than or equal to norm A. Oops. That's a little c, by the way. There's a big C. And the similar thing for B. And again, this norm 3 could be any norm. So this is just with the definition. This is true. There exist these constants such that these inequalities are true for all vectors x. We can combine this stuff. So what I'm going to do is let's look at, just make sure I'm doing this right. So I'm going to multiply basically I'm going to be taking sorry, I'm just seeing what I did and trying to figure out how to express it. All right, so basically I'm going to somehow combine these because we want to show that a similar type of statement is true, except instead of x3 and xa or x3 and xb, it's xa and xb. So we need to find these constants. They're going to be based on these other constants. So if I multiply this top thing through by cb over ca, and I really only care about the right side for the moment. So if I take this right side, so because of, here, I'll call this statement A, statement B. So statement A implies we can write, if I multiply by little cb over big ca to both this term and that term, this is a ratio of positive numbers. It's not going to mess with the inequality. When I multiply by the second term here, the big CA's are going to cancel. I'm going to get little cb x3. That was my want, because I know that this is less than xb. Norm xb. Norm b of x. And then I can do a similar thing. I'm just going to do this all in one line. If I do a similar thing on these two terms, I multiply by, let's see, what's it's going to be, big CB over little CA to get this to cancel out. Then I'm going to get, so I know this is less than or equal to big CB. Oops, need my pen. Didn't work. Here we go. So this is less than or equal to this, just from here. I keep having to pan. Wish I could set it to pan with my fingers and write with my pen. Maybe I can figure out a way to do that using a different whiteboard, but anyway. If I do the same sort of trick with here where I multiply by CB over little ca, then I'm going to get CBX3 here, which will be less than or equal to big CB over little ca xa. So I multiplied these two through by CB, big CB over little ca, to get this. And then I already know this is less than or equal to this. And what I've got at the end, you know what? It's time. That didn't work. Let's try it again. I get these two numbers. these two constants, we found that they exist. We know this is true. We've got the xb in the middle. It's this constant times norm a of x, this constant times norm a of x. These two are equivalent. A and b are equivalent. We've sort of bypassed this x3. As you can see, I didn't use anything about the norm of x3. I didn't have to call it x3. It could be any norm. This shows that norms are transitive. Cool. Step 1 done. Let's go back up. Step 2 is to prove that we only need to consider the unit vector. But before I do, notice this. Because of this equivalence, we only are going to need to show, because of this transitivity, I was thinking equivalence relation, but this is called equivalence. It's a bad choice of words on my part. Because of this transitivity of equivalence, we're only going to have to show at the end of this that norm 1 is equivalent to norm 3. Because it's a generic norm, if we can show it's equivalent to norm 3, then we would use the exact same method to show that another generic norm 2 is equivalent to norm 3. And this result tells us that norm 1 and norm 2 are equivalent, if that happens. So if I can show that norm 1 is equivalent to norm 3, we're done. We're done. I should probably write that down. It is important for the logic of the proof. I won't explain it all the way through again, but you know what? Let's change up the color. It suffices to show that norm 1 and pan norm, started writing norm 3 are equivalent. But you can do that, we're done. Equivalent. Get the idea. All right, so now we're on to step 2. We want to show we only need to look at unit vectors instead of all vectors x. So assume there exists C, well, we do it the same way I've been doing it. Big C less than little c less than 0. Such that this equivalence statement for some x, for some norm A. Is there any reason why I can't just go norm 1 now? There isn't. Going off my notes, if I say norm A, I mean norm 1 in this part. Losing my place. So we're going to assume that this is true when the length of x in norm 3 is 1. And we're going to show it is true for all x. All right, so the goal of this step again, just to reiterate, we're going to show that if it's true for your unit vector, it's true for all vectors. Then we're only going to have to show this is true for unit vectors. a unit sphere, if you will. And that'll be doable. Let me get back to my notes. Okay. Let U equal x over the norm of x3. This is your classic way we would make a unit vector even in your introductory, like linear algebra or high school even. But let's show that this has length 1 for all x, then we'll be good. That would mean we'll be able to take any x, turn it into a unit vector, and if it's true for these unit vectors, it's true for all the x. Anyway, let's look at it. Then the norm 3 equals x over norm 3 of x. This norm 3 of x is just a number by one of our properties of norms. Gotta scroll back a bit. Oh, it's right here, number 2. We can take that out and absolute value it. Although since it's a norm, it's already non-negative, so we can just take it out of this other norm. So this equals norm x3 over norm x3, and number divided by itself is 1. So the length of this is 1. Even in this other, well, in any norm. I didn't use anything particular about this norm. Anyway, this is a unit vector. But anyway, if we have a unit vector, its length is 1. So if I look back at this right here, this is 1. This is, sorry, if we have u. If I put in u, this will be 1. This will be 1. We're going to get, bear with me, we're going to get that c is less than or equal to u 1 c. If I plug in u to this becomes 1, this becomes 1. We get that. This will be our condition that we look at later, but let me actually put the x's back in. Or the u's back in. I want to put the x's back in. This is another spot where I'm probably not explaining it super well. So apologies for that. Put the u's back in. Now I'm going to use how we defined u to put those back in. And I'm going to go ahead and use this little trick here as well, because we already did this. But that trick works on any norm, not just, these don't have to match. This is norm 1 like it is here. We can still, this is just a number we can still take out. So, right, we can take that, I mean, this is what we're going to get. This is what we're going to get. these in the wrong spots. All right, so just applying this thing to each of these, we get this. We can multiply through by the norm of x3. It's a non-negative number. Let's go ahead and assume that x is not 0. If x is 0, then this is just equal anyway, so we're fine, no matter what c's are. And we get what we want, I believe. Is this what we want? We get c. Oops. We get c norm x, norm 3 of x less than norm of x, norm 1 of x, less than or equal to big C, norm 3 of x. We get that 1 and 3 are equivalent for all x. We only assumed they were equivalent for these length 1 unit vectors. But for every unit vector, make sure I can see my camera. For every unit vector, if you think of, probably shouldn't do this in 3D, but if we have this unit sphere, if I pick a unit vector, any vector in that direction, we can just divide by its length to get that unit vector. Tried to point into the screen. Okay. So this is saying for those same values of c, little c, big C, that big C is like smaller than that little c. Apologies. It's true for all x. Anyway, part 2 is done, I think. It seems good. But basically what we've done is we just need to find this. We have this. All of this we've already done the legwork for. That doesn't seem so bad. That's why we use this particular norm, because of how this works out so nicely. That's one of the reasons. Actually, it doesn't have to do with this norm. I was wrong. Because the unit will also, anyway. Yeah, I don't think it had to be norm 3 again. We didn't use, yeah, it didn't have to be norm 3. This is true for any 2 norms. If any norms are equivalent for its unit vectors, it's equivalent for all of its vectors. Cool. We're halfway there. It's already after 1. Next 2 steps actually shouldn't be too bad. My coffee is getting cold though. Okay, step 3. We want to show, I'll reiterate, show, we end up making my notes up. I'm going to try to use norm 1s again. But this is should be work for any norms. Come on. All right, so we just want to show that norm 1, which is just any old norm, is continuous under this specific norm 3. So we do actually need the norm 3 specifically. All right, continuity is something I still kind of struggle to understand. I didn't spell continuous right there. Not gonna fix it. No time. I'm gonna have a cursor in this image. Continuity, how you learn it in like high school, is a bit squishy. I should say high school or college, undergraduate calculus. uh, this is this definition is more precise. All right, so let me make sure everything is visible fine. It is. So a function going from x to y is continuous at a point x in our domain if for all epsilon greater than 0. So if I give you an epsilon, it can be super tiny. It could be like 0.001. There's got to exist some other number, delta, such that... Actually, I'm going to skip this first part with the balls, so I don't have to talk about it. D is just a distance. A norm acts as our distance in this case. So just treat these D's as distance. So there exists a delta. I give you an epsilon, there exists a delta, such that for all points in our domain, the distance between our point x and that point y, for all points that are delta away from x, you could. That's why the ball. These are balls. That's why balls make sense. Just for delta away from x, then our distance in our codomain here, if we run it through f, is less than epsilon. Basically, I give you a distance I want our outputs to be within, and I say, okay, as long as my inputs are within this other certain distance, we're good. And then continuity just has to be continuous at every point x. Anyway, let's keep going. Maybe I'll do more copying and pasting than writing, but that's harder to follow, maybe. But I'll do it for this part. I'll jump back into writing after my first little statement here. So I typed up all this earlier in the week when I was figuring it out, because typing it up keeps it for me so I can study off of it later. As well as it helps me crystallize make sure what I'm saying is actually makes sense. Okay, so translating this into our situation, we want to show that for all x in Rn, because Rn is where we're starting from. We're in from Rn into R. I'm not going to scroll up, but that's when we looked at what a norm is. It goes from our vector space. Our vector space is Rn in this case, and we're heading into R because it's a norm. But we're saying that how x works is norm 3. We're saying we're measuring distances in Rn by norm 3, and our function is norm 1. It's a little confusing, but it's more of a tracking thing than a conceptual thing. We're going to measure our distances in Rn by norm 3. Our function is norm 1. Okay, so we want all x in Rn. We want for all epsilon greater than 0, there exists a delta such that, oh, that should not be x. That should be Rn again. Sorry, copy paste error there. I copy pasted this and put in everything. So for all y in Rn such that, oh, of course, since I copy paste, I've got a's instead of 1s. I can just, I want this to be 1. This to be 1 now. All right, such that our distance in Rn, which we're measuring by norm 3, so just x minus y is the distance between these 2 points, is less than delta. We want if we run each of these points through our function, which is going to be norm 1, we want the distance between those things. In R, these are 2 numbers. We just want their absolute value of their difference to be less than epsilon. Oh boy, feel free to go back and think about this. But basically, we're going to start with everything up to here, and we want to prove this thing. Okay, we're going to assume all that. We're going to prove this. although we need to find this delta. We're kind of going to go through some calculations to see what the delta is first. So we're going to look at what this is. First, we're going to look at if we lose the absolute value here, we take x1 minus y1, and then we do a fancy little trick where I'm going to call this first x y plus x minus y see that in here this is just x because I got a plus y and a minus y, and I was pointing wrong spot. See in here this is just still equal to x because I got a positive y and a negative y, they cancel out. But then we're going to apply the triangle inequality to this specifically, but then this whole thing will be greater than this whole thing. So we get y plus x minus y minus y. Now our y, these cancel out. Got a pan on my tablet. So this equals x minus y. In the interest of time, we can do a similar trick. Should stop moving this around when I want to move this around. We can do a similar trick for y minus x and get the same thing. Similar trick, keep scrolling the wrong thing. Similar trick, get the same outcome. Therefore, the absolute value of the difference, because it doesn't matter which ways we subtracted them, if we get the same thing, then the absolute value of the difference is equal to this value. Sorry, it's less than or equal to because of the less than or equal to. So we get, I'm going to write that down. That's an arrow. We get this minus this is less than this minus this. All right. Now we're going to use the triangle inequality on this norm. We assumed it's a norm, so we can use the triangle inequality on it, just like we did up here. And what we're going to get, I'm going to copy paste this as well. Oh, but there's so many A's. I'll just write over them. This will be messy for me to write anyway. Okay, let me get this zoomed in, make sure my face isn't blocking it. It's not. Let me fix these A's into ones. Should have just stayed with A. Sorry for the messiness of that. All right, so triangle inequality. First, this first step, just like we did when we were proving that norm 3 was a norm. We just use the definition. We're using the same basis of E1 through En. Any basis will work as long as we're consistent. And then we do the same sort of thing where we group them together. We don't have a definition of norm 1, but we can use a triangle inequality right here. So right here is the triangle inequality. So we're saying that this sum all together, all normed, is less than or equal to if we norm each piece of the sum and add those up. So that's fine. A minus b is a number, so we use that second property again to take out the a minus b, and it's make sure we have the absolute value on it. Now, we're just looking for like a restriction. This delta is just a restriction we're looking for. So we're going to say, okay, whatever this is, if we change EI to whatever the biggest one of these is. In whatever in this norm, whatever the longest basis vector is, if we switch out each of the lengths of the basis vectors, these are just numbers, we switch out the biggest number, or switch in the biggest number for all of them, then we'll get something bigger. It's got to be, I mean, unless they're all the same size, then it's going to be equal. But if they're not all the same size, it's going to be bigger. So we get less than or equal to, switching in the biggest length of a basis vector. But what that means is we can pull out this number, this max is in every piece of this sum. We can pull it out, and what we're left with is a sum of numbers, absolute values of numbers. This is the same as the norm 3 of x minus y. These were our x coefficients, these were our y coefficients. And so this, by the definition of norm 3 that we defined way up top, we just get this, and we pulled out this max, so we get that in the end, this absolute value of norm 1 minus the absolute value of norm 1 of x minus norm 1 of y is less than this puppy. Whoa. Since I've been going for over an hour, I'm going to keep copying and pasting, which means I have to keep replacing A's with I's. Too big. Too big. That's fine. Let's move it up. Okay. So we're going to choose our delta to be epsilon over the max here. The max length of a basis vector. The length in norm 1. It's really ugly. Oh well. Then we're going back. We're going to assume that this is norm x of x minus y. Let me go back here. We need to assume this. In norm 3, we were using the distances of Rn under norm 3. We want to show that this is true. So we kind of like used it to find a good delta. Now we're going to go back. We're just going to assume that our norm 3 distance is less than this delta. We're going to show this result, and we should have engineered it to work. It is not the sandwich theorem, but it's kind of sandwichy. It's like a hot dog, I guess. All right, so if this norm 3 of x minus y is less than delta, I'm just going to replace in our value of delta we picked. Then I'm going to rearrange so that I'm just going to multiply both sides by this max. But then this is greater than this. So that means this has to be less. If this is less than epsilon, then this is less than epsilon, because we said that this is greater than this. So we're done. It's continuous. I'll tell you what theorem we are going to use. It's the extreme value theorem. I'm going to fly in from my notes, and there's an exclamation point because my professor said, hey, don't forget this theorem. We didn't call it the extreme value theorem. I found that when I was looking up this proof. It's like, use the extreme value theorem. Then I searched my typed notes, extreme value theorem, nothing popped up. And then I was just looking through this stuff to try to find it, and oh, we just didn't call it that. Anyway, so if we have a compact set, get to that in a second, and a continuous function is what this means into the reals, which we do. Norm 1 we just showed is continuous. Oh, this is We're on step 4 now. Then f is bounded. I don't think we need that now, but f achieves its minimum and maximum. That'll be important for us. So what we're going to do, this thing has literally 4 more lines. We're almost there. So compact just means a closed and bounded set. A closed set just means that there are no, if you take any limits in of like sequences of points in the set, you're gonna get the limit of that sequence is gonna be a point in the set. So we can think about here. What just happened? On my tablet it just jumped. So if we think about, like, here's a classic example, just like a closed ball is, even if I just think about the circle, whoa, you're about to see something weird in a second. Oh, it didn't pop up. Although I guess for the moment, let's consider the points inside too. So if we have all the points inside this circle plus the boundary versus all the points inside this circle minus the boundary, this is a closed set because any sequence of points in the set are going to be tending toward another point in the set. However, in this set, I could have a sequence of points heading toward the boundary, all the points being in the set, but the limit being on the boundary, which is not in the set. So this is closed. This is open. So we're going to consider a unit sphere. Kind of like this first one, except we only really need the boundary itself, which itself is a closed set. And this is in n dimensions, not 2 dimensions. So all these unit vectors such that the length in norm 3 is 1. It's closed because it's just like this. It's a collection of points where all the points are this surface of a sphere, really. So any sequence of the points gets us another point in that surface of the one sphere, or sorry, of the radius 1 n sphere. And it's bounded because it's a sphere. It's not going off toward infinity. One way to define boundedness is to be like, we can put it inside a sphere. So we can put it inside a slightly larger sphere than itself. We're fine. So this is closed and bounded means compact. So this is compact. And we have that norm 1 is continuous. So we have the things that we need for this function. So that means norm 1 achieves its minimum and maximum somewhere in this set, this sphere. So we're going to let little c be the minimum over this unit sphere of passing u through norm 1. And big C is the same, except max. So we know these exist on the unit sphere because of the theorem. We're going to call our little c the min and our big C the max. But that means thus C is less than or equal to norm 1 of u, which is less than or equal to big C. Little c was the minimum of all of these. Big C was the maximum of all of these. We got to have this, and we're done. We're done. Because we know if this is true, scroll all the way back here. We know if this is true, then norm 1 is equivalent to norm 3. And because of part 1, that's all we have to show. Because we showed that some general norm 1 fits, we found values of little c and big C such that norm 1 satisfies this. And that means, because of all the groundwork we've done, that any two norms, finite dimensional norms, are equivalent. Okay, a little over an hour. I had to do some of the copying and pasting, but I had that as a backup. That's it. My goodness. Well, that's useful for me. Oh man, this just looks like a smiley fry. It's making me hungry. I don't think there's a fill tool on this. I had this banner down at the bottom because there were ads, yes, that on this website usually, and I was going to cover the ads. And then today there were no ads. I don't understand. Anyway, yeah, I guess I was like an hour and 15 minutes. Thanks, bye.